Yes, my name is Zerrin Yumak. I'm an assistant professor in the Human-Centered Computing Group. And I have been working a lot on the area of socially interactive digital humans, but also earlier on physical social robots. So today I'm going to talk about how we can create virtual characters automatically using AI-driven algorithms and how we can generate interaction for them. So this is the outline of the talk. The first part of the talk, mainly 70% of the talk I would say, will focus on animation from a 3D graphics point of view. How we can model the characters and then make them move. So I will focus on a short introduction of body and facial animation. And later I will switch to the part on non-verbal behavior synthesis, which is my major area in terms of animation generation. So it's also called social animation, in particular generating facial expressions, gestures, and gaze behaviors. The second part of the talk will focus on interaction, so more on AI and HCI, human-computer interaction perspective, how we can make these characters conversationally interactive with us. So I will introduce the sensing, decision-making, acting loop, and I will introduce some of the work we have been doing in my lab on modeling emotions and memory and also multi-party interactions. Okay, so let's start. So if you look at the state of the art of digital humans, we started to see very impressive examples nowadays. These are some of the recent examples from Unreal Engine MetaHumans. So being someone working on the digital humans area for 15 years, this state is very exciting, very impressive at the moment. The last couple of years, we reached to this state, and it's accessible in game engines at the moment, and we can really push the boundaries of realistic, natural interaction with digital humans. We started also to see these characters in games. I just want to ask quickly, who are you familiar with a few of these games? Yeah, okay, I see people nodding. For example, the game Detroit Becoming Human, it includes very realistic virtual characters. These characters are especially used in games with a realistic storyline. And on the other hand, there are other type of applications where you can see a range of appearance and animation quality. So on the one hand, there are very realistic games, but you can also have, for example, VR simulations that are focusing on specific problems, such as the one from Tailspin. It's a Dutch company, also based in Silicon Valley, which is generating simulations for non-verbal communication skills training, in particular soft skills. For example, job interview scenarios, or another one, another Dutch company, the Simulation Crew. So then you can see in that kind of applications, the appearance quality and animation quality of the characters are a little bit different. And on the other hand, end of the spectrum, we also have, for example, in social VR, Facebook, Meta virtual characters, or Microsoft Teams. So we are not very impressed yet with the appearance and animation of the virtual characters in Meta. But the idea here is that, of course, when you start to have platforms that are with many users, of course, you have to make some choices. But there is still a lot of things to be done in that area in terms of improving the quality of the movements and the appearance of these characters. And also deciding on in which platforms, which kind of characters will be interesting to use. For example, if you are using a meta type of very cartoonic characters that are reporting from a war zone, that will not be very convincing. So you have to make certain choices, what kind of characters will be convincing in certain contexts. So now I want to start a little bit in terms of like an introduction to body and facial animation. I'm not sure whether you are a little bit aware of these topics or knowledgeable, but the word animation, according to the Merriam-Webster dictionary, it means to give life to. It's based on the Latin word anima, meaning breath and spirit, so you can also find it in the word animal. And animation is the process of making illusion of motion. So we are all familiar with cartoons from our childhood. Computer animation, on the other hand, is computer-based imagery computation used producing images intended to create perception of motion. So there are not so many, there are quite some books on keyframe animation or artistic animation you can find on Amazon everywhere, but there are not so many books on the technical aspects of animation. This is one of the very good books from Rick Parent, and if you want to step into this topic, I would highly recommend to start with that. We can classify the animation in three high-level categories. The first category is artistic animation, so where there's an artist that crafts the motion using keyframing and interpolation, so that is a very time-consuming area. A second category is data-driven animation, where you use motion capture devices and use machine learning AI algorithms to regenerate motion. And the last category is procedural animation, where you use computational models of motion by setting, for example, conditions for physical and behavioral simulation. So it's really mathematical simulations. I'm mainly working in the second category, data-driven animation, but depending on the application, I also have to use the first one or the third one. But my major area is motion capture and AI-driven animation synthesis. Okay, motion capture. It's possible to collect data with motion capture devices. There are different type of devices, for example, optical motion capture. And there you can have passive, active, and markerless motion capture systems. Here you see an image from our motion capture and virtual reality lab, where two of my students, master students, are interacting in a full face and body tracking suite. Using a passive marker system. These are retroreflective markers. They are like small dots that you attach to the body of the actors and actresses. But the community is also moving more towards markerless motion capture, which is very useful for situations where you want to capture people outside. For example, if you want to capture people in a sport, in a game, and you don't want to rely on very high investments, bulky systems, then it's the way to go. But on the other hand, these systems, computer animation pipelines, are still very, very useful if you want to generate high quality animations for games and VR. And of course, you can also use inertial systems with accelerometers, gyrometers, etc. So how can we represent virtual humans? Virtual humans are represented with a skeletal model. In the image here you can see, maybe it's visible, there's a mesh, it's a polygonal mesh, and then inside the polygonal mesh there's a skeleton with a lot of joints, and these joints are structured in a tree hierarchy, starting from the root node, and then as you move the upper parent nodes in the hierarchy, the skeleton is moved. So as you move one bone on the hand, the vertices that are surrounding the skeleton are also moved along. So you can consider the skeleton as a low-level representation of this polygonal mesh. And for a character, you can define different degrees of freedom. For example, for this character, you have 3 translational degrees of freedom and 48 rotational degrees of freedom. And depending on the joint, you can have, for example, for the knee, 1 degree of freedom, for the wrist, 2, and for the arm, you can have 3 degrees of freedom. And you can put constraints to decide on how much these bones are going to move. So if you want to define animation, you just need to configure this over a timeline, basically. There's a closer look at the skeleton hierarchy and the polygonal mesh surrounding it. As I described, as you move one of the bones, the vertices in the mesh moves along, and this process is called skinning, and skinning is an important industrial but also research problem. So if we summarize the skeleton posing process, it will be composed of 3 stages. The first stage is where you set all the degrees of freedom, which is defined by a high-level animation system. For example, if you're working with Unreal Engine or Unity, you tell your character to do a certain action, for example, walking or dancing, and all these degrees of freedoms are defined by the high-level animation system. And then they are sent to the rigging system, which is the skeleton and the skinning of the character. And you apply a recursive traversal through the hierarchy from the root node and use forward kinematics to compute the world matrices, because we have to compute everything in world space for computer graphics. And then after the rigging system, change of the skeleton, these world matrices are used to deform the skin, which is done by the skinning system, and finally sent to the renderer. Traditionally, skinning algorithms are based on linear blend skinning, or it's also called smooth skinning algorithms. But these algorithms have some limitations, as you see here in the examples. This is called the skin collapse or bending effect, or candy wrapper effect. Because of the linear interpolation, you lose some of the vertices here, and these kind of limitations are later solved with the introduction of dual quaternion blending. Dual quaternion blending is a special type of mathematical representation where you can represent both rotations and translations together in terms of quaternions, which allows you to do better interpolation. Instead of linear interpolation, you can use spherical interpolation, for example, and which resulted in better improvements on the skinning algorithms. And currently, in most 3D modeling tools, such as Maya and Blender, you find a version of this kind of dual quaternion blending algorithms. As I said, it's a large topic, so I will not really talk about a lot in the skinning topic, but if you are interested in that type of research, I would highly recommend this SIGGRAPH course about skinning, where you can see different type of methods, including direct methods and data-driven approach. So that was so far body animation. I would like to also talk a little bit introduction to facial animation. Different from body animation, facial animation is quite difficult because face is a very complex structure. Anatomically, it's composed of a lot of tissues and as well as bones, and they're also very familiar to us. So if something is off on the face, we are very much attentive to that, and we immediately realize. That's because there is this effect called uncanny valley. When we look at digitally produced faces, we are very much affected if something is not done properly. There are different type of ways to capture, to generate facial animations. Of course, traditionally, if we are doing it with keyframe animations with a huge team of artists, and it's very time-consuming and costly. On the other hand, you can capture facial animation with 4D scanners, which produces quite realistic results. But the challenges there is you have a point cloud data, and you have to, of course, register a mesh to it, and then fit a skeleton, or create a wide range of blend shapes. But still, the facial deformation itself can be nicely captured with this kind of methods. I mentioned about the uncanny valley theory. Who is familiar with this concept? Okay, a lot of people, but I will briefly touch to that. So this is a concept originally coming from robotics, actually, but also used for digitally produced characters. So as the human likeness of these characters are increasing, the affinity, or let's say the likability of these characters increases to a certain point, and there's a sudden drop, which is called the uncanny valley. And it has been quite a challenging problem to go over this valley in the robotics and digital humans computer animation area. But recent research work, for example, from 2021, ascending from the valley, can state-of-the-art photorealism avoid the uncanny, started to show signs of passing over this uncanny valley because we started to produce very, very convincing digital characters. The basics of facial animation, the widely used methods is blend shape animation. You can consider a facial model, for example, composed of 100 blend shape, of thousands of blend shapes, depending on the complexity. And from an industry term, these are called slider values or blend shape targets, but from a math point of view, they are weights and basis vectors. So you have the blend weights and the blend shapes, and you take a sum of these and you can combine a resulting face. So you have a, let's say, 100-dimensional space where you combine all these different type of expressions, such as happy, sad, angry, or maybe mouth movement, and you create the finalizing resulting face in this multidimensional space. Of course, because it's a multidimensional space, you can apply all kind of data analysis algorithms on this space, such as dimensionality reduction. One big challenge is, of course, how to construct these blend shapes. There are different type of methods to do that. For example, in Lord of the Rings, there were 675 morph targets or blend shapes, and usually skilled artists, they form a mesh. It can be scanned from a real actor, or we can use 3D construction from images or using 4D scanners. Apart from blend shapes, one other technique that has been used was parameterization of faces. Because faces are composed of a lot of vertices and it's a complex topology, people were thinking, how can we represent them in a low dimensional space? In the early days, for example, there were MPEG-4 facial animation parameters and facial definition parameters. There's also other standards. This is just an example, such as facial action coding. But for low-cost transmission, MPEG-4, for example, was used widely in the earlier days. So in the image, you can see the arrows here represent the facial animation parameters, and the points which define the facial 3D face geometry. These are the facial definition parameters. So I mentioned about data-driven and procedural approach. So one way of producing speech animation for the face is a procedural animation. So what you can do here is you can find the building blocks of audio or text, which are called the phonemes. And for each phoneme, you can create a mapping with them. These are the visual counterparts of phonemes. And at a very simple level, you can just interpolate these phonemes to create the finalizing lip-synchronized speech animation. It sounds easy, but in practice, it's not really working that straightforward, because there's a phenomenon called co-articulation. When we are talking, these phonemes are overlapping to each other and affecting each other, as well as the rhythms. That's because it's quite difficult to capture these realistic representations of the lip-synchronized speech. And actually, the speech animation community and the graphics animation community is focusing on this problem for several years now, and it has not been fully resolved. Still, there are still work that is pushing the boundaries on making the lip-synchronized speech very, very realistic, because it's also very personalized, depends on the person, the language used, etc. Procedural approach in the early days were not working very well, because they were mainly based on rules that were derived from linguistic studies, and they were not producing very convincing animations. That's because data-driven approaches were introduced. But in the last couple of years, there were kind of a striking back from this procedural approach line of research. So one example here is Jolly. Here they were using lip and jaw movements separately to create realistic lip-synchronized speech animation. And this research work, which was SIGGRAPH 2016, also became a company later, and it was used in a lot of games, such as Cyberpunk, for example. On the other hand, there are other methods which are data-driven, so you can learn co-articulation, and lip-synchronized speech animation from data. This is one of the early works dating back to 2005. So the data-driven animation is rising in the last couple of years, but it's not something completely new. There were a couple of works that has been done in the last 15 years. So in this work, the system takes an audio of input sequence, and there's an animation graph, or it's called a motion graph technique, where you create building blocks of the animation that was captured with the motion capture device, and then you combine and stitch them together later using a sophisticated algorithm. There is an emotion classifier to understand the state of the emotion from the audio input sequence, and these are combined to create expressive lip-synchronized speech animation. If you look a little bit more closely to the architecture here, so I mentioned about anim graph or the motion graph, so you can see here there's a node for the representation of each of these small chunks of motion, and each of them is composed of 4 components: the phoneme label, trajectories of the procedure features that are coming from the audio, compressed animation motion, and the emotion label. And on the other hand, you can do phoneme labeling and extract the features regarding the emotional state, maybe it's happy or frustrated. And then you can use this information to do a constrained graph search algorithm to, at the end, generate an animation sequence that is following these constraints. For example, your constraints could be to find the right path that is satisfying a certain emotion or smoother animation. So these were mainly based on optimization-based algorithms. In the years around 2013 and onwards, of course, these were the years where Kinect and depth cameras were very popular, and people started to look into video-based facial animation. The earliest work on this is online modeling for real-time facial animation from SIGGRAPH 2013, and we have seen different variations of this work in the following years. So using, for example, a video camera, single video camera, using a mobile phone camera, etc. And these works also led into a company called Phase for markerless motion capture, which is now part of your iPhone. So data-driven, audio and text-driven face and body animation is a very fast-growing field in the last couple of years, thanks to the improvements in machine learning and deep learning. So in the first maybe 20 years ago, there were sporadically some data-driven work, but in the last 10 years we started to see a lot of work that is based on motion capture and data-driven methods, also video-based, of course. But I will mainly touch here the 3D motion synthesis approach. So we started to see, for example, gesture animation, also taking into account personality or emotional characteristics of the people, audio-driven animation, face former, and from Taylor also. As well as generation of animation using 3D vertices, scanned data using a variety of methods from convolutional neural networks to generative adversarial networks to transformers, etc. Another work detects automatically the eye movement given a motion capture, body animation. And also recent work is looking into not only single character animation synthesis, but generation of animation in 2-party or multi-party interactions, which is an open and active area of research. Okay, so far I have been giving some introduction and state of the art. In the next couple of slides, I would like to show the work that we have been doing in my lab. As I mentioned at the beginning, I'm mainly focusing on nonverbal behavior synthesis. So I'm interested in social animation, although in general I'm teaching machine learning and deep learning and computer animation for other tasks as well, such as locomotion. but my main interest is social interactive characters. So if you look at nonverbal behaviors, this is a topic that is of interest to different communities. A social signal processing community is working on this area mainly, but also it is subject to interest in virtual worlds and animation, and of course the communication and interaction between these communities is very fruitful. The first work I would like to mention is audio-driven emotion synthesis. So this was a work we have done in our group to generate lip-synchronized animation that is detecting also the emotional state in the audio. The main goal was to create a system that is controllable, so that's because we went for a procedural approach, and naturalness of the animations was also desired, so we were pushing this direction as well. Here we can see an overall architecture. So this system is taking an audio input. We parse the input for detecting the phonemes and visemes. And we have two components, expressive speech animation and dynamic co-articulation, where we take into account pitch and intensity values in the audio to dynamically change the intensity of the particular visemes. So we were creating a kind of a rule base because it's a procedural approach. And we generated as a Unity plugin and applied it to realistic characters. We made some comparisons to existing tools. At that time, this is a work from 2019, so at that time we had FaceFX and Rogo Digital commercially available in the market. And we indeed found out that introduction of the emotional speech animation and finding the emotional cues resulted in better perception of the animation, and the users perceived the animation quality better in comparison to FaceFX and Rogo Digital. We are also working on data-driven facial animation. So, for example, we have been looking into mocap data using generative adversarial networks to find the control space of emotion. Also facial retargeting using radial basis functions and comparing with sequential models such as recurrent neural networks. And we are collecting data in our motion capture lab for facial animation in order to further analyze and generate more convincing animations. A recent work that we have been doing is FaceX Hubert. The work is aiming at textless speech-driven expressive 3D facial animation synthesis. My PhD student, he is also sitting somewhere here, so he's going to, yes, there. He's going to present the poster about that tomorrow. So if you want to hear more about the details of this work, you can talk to Kazi later. But I will show a short video here. What you will see here is the first is a neutral face, the second one is an expressive face, and the last one is showing the difference between these two in terms of heat maps, so that you can see how which parts of the face is activated. The method was trained on a 3D scan data set with various actors, I think 40, something like that. And we tested it also with any type of audio, for example, extracted from movies, etc., to see the generative capacities of the model. So let's have a look at it. I hope the audio will work.
Stuff? Oh, okay, I see. You think this has nothing to do with you. You go to your closet and you select, I don't know, that lumpy blue sweater, for instance, because you're trying to tell the world that you take yourself too seriously to care about what you put on your back, but what you don't know is that...
Okay, so that was, Meryl Streep talking from Devil Wears Prada. So we tested it with different kind of audio to see how it works. Also singing animation, so there's a full-fledged video you can just go and watch. It's pretty entertaining. We were using techniques such as Hubert encoder and transformers and gated recurrent unions to generate automatically the facial animation. We were not only working on AI-driven animation generation, but we are also looking into how these animations are perceived. This is a study on perception of appearance and animation of virtual characters. That was a study that was done by one of my master's students. So what we did for this experiment is we created very realistic faces, but also low fidelity appearances. This is using Unreal Engine MetaHumans. And we also created 3 levels of animation fidelity. And we were creating these conditions and looking at how people are perceiving these animations. For example, the effect of uncanny valley, how eerie the animations are perceived, what is the effect of social presence, etc. So we simply created some videos that are generated in different emotional conditions, such as happy, sad, angry, and neutral. And we asked the users to rate how natural and believable these animations are perceived. So what we found that there's the mismatch of motion realism and appearance realism led to significantly higher eeriness. This is an indication of uncanny valley. So if there's a mismatch, if you have a very realistic character and then an animation that is not done very properly, that will result into a disturbing feeling. So if you want to push your application to a level that you want to use very realistic characters, you should be really careful about that, because if the animations are not matching the appearance, it can be really, really disturbing for the people. Higher appearance realism led to significantly higher social presence, which was expected. And for full motion realism, higher appearance realism led to significantly higher social presence. There are a lot of analysis from this study. I will not really go into all the details, but I can share with you the work for more details. What we can conclude from this study is that state-of-the-art photorealistic appearance lends itself better to highly realistic animations than lower appearance realism. So as I mentioned, it's very important to be careful on this match between high appearance realism and animation. If you have a character that is not very realistic, you don't maybe need to do very complicated animations for that character, or vice versa. In addition to facial animation, I have also worked on gaze animation. This is a work that has been done in collaboration with Guerrilla Games in Amsterdam. They are developing beautiful games such as Horizon Zero Dawn. I had a student working there, and Guerrilla Games asked us how we can improve our procedural gaze animation methods and come up with something better. Can we try, for example, a data-driven animation approach? So we took the challenge and we collected data in the motion capture lab. You see an actress here. The actress' gaze behavior is captured. So gaze behavior here is defined as the upper body movement, and the actress is following a target object in the 3D space. And here, my student Alex has this stick, and then at the end of the stick there is a small marker, and the actress is following that. So this is called the gaze following behavior, and we would like to replicate this behavior with these virtual characters, where the character is following this beer mug. And we were using a sequential model, a gated recurrent unit. So the pose and the target object location is given into the network, and the network is trained, and in the output layer it was generating the rotation values of all the upper body joints. There were like 20 plus joints. We also did it for low level of detail and high level of details characters in games. And we found out that in comparison to the procedural approach, we got pretty good results. So as expected, data-driven approach work much better. And we captured the situation standing, sitting, and laying. So there were three different conditions. But as you can see, there are still some problems in the animation. This is there are moments that is smoothly following the target, but there are moments it's also very jittery, the animation, and then it's not really learning the correct motion. So there's still a room for improvement. But it was a promising result to show that gaze animation is also a promising area to pursue over procedural gaze animation generation. We were also working on expressive gesture animation, so in particular in the context of music-driven expressive animation. So we were working with motion capture data that were collected by piano players. From piano players, and this was a long short-term memory network where we had the musical features and the body position, and in the end we created the upper body position for this character, and we were comparing different metrics in the audio such as pitch, beat, MFCC, etc. with different kind of metrics such as average position error, acceleration, and jerk, which are representations of smoothness of the motion. I'm going to show a short clip here as well. This dark character is the generated motion here, and the pale one, I'm not sure if you can see, is the ground truth motion. Okay. So we were also working on nonverbal behavior synthesis in multi-party group interactions. That was also a collaboration with a company, Clev VR in Delft. And we would like to generate automatically turn-taking behaviors, conversational behaviors for characters that are in the background in the game. So the purpose was not to create very realistic motions here, but we were working with Carnegie Mellon University Panoptic dataset, which is a dataset that was captured with depth cameras, and then from this you can extract the skeletons. And then we were analyzing and annotating the turn-taking states and using a Bayesian network, so a probabilistic method to automatically generate the gestures. And here you can see, for example, there's a red dot. Whenever the character is speaking, you can see how the turn-taking is dynamically happening between the characters, and also the gestures are generated. So in terms of the state of the art and pushing the boundaries of animation synthesis, we are at the stage where we can consider multi-modal and multi-party animation. So here you see a video clip that was captured in our motion capture lab. Two students interacting with each other in a daily conversation where we captured the whole body, fingers and face all at the same time. We collected 10 hours of data, and now our goal is to generate more methods taking into account multiple modalities and to see also what is happening in two-party conversations. I will now talk briefly in the remaining part of the talk the interaction topics. So far what I was talking about was the synthesis of animations and behaviors, but social interactive virtual characters also started to become very much attracting attention in the industry, such as Samsung Neon and NVIDIA Violet, the company Soul Machines, etc. So we started to see a lot of companies focusing on social interaction. If we look at a very high level what is happening in socially interactive characters, the first stage is understanding social and affective cues, the middle stage is decision making and dialogue, and the last part is generating social and affective cues. And if you want to do fully autonomous virtual characters that are socially interactive, we require a quite range of capabilities: expressing and perceiving emotions, communicating with high-level dialogue, using natural ways of communication, establishing, maintaining social relationships, having a personality, learning, recognizing models of others, and learning, developing other type of social competencies, for example, walking, following behavior. So this is a list coming from the social robotics community, but well applies to intelligent virtual characters on the screen as well. But as you can see, these skills are very, very complicated. I often joke about that to do such a character, you need the whole computer science department, and it's also not enough. You also need the other disciplines, so it's quite a challenging area. If you pick one of these topics, it's already a huge. So if you want to go in this direction, be careful what part you want to really focus and the feasibility of the things. I can give some tips on that as well on the coffee break if you're interested. So what I have described so far in the first part was only focusing on this last box, generating social and affective cues. But I have been also working doing some work in these first two boxes. So I will show some examples of this. This is something that I have been doing quite some years back about modeling emotions and memory. So how can we give remembering capabilities in an emotional context in social human agent or human-robot interaction. This is a fully fledged autonomous system with face recognition, speech recognition capabilities. There's a dialogue manager with a planner and reactive layer. There's episodic memory, which is a special type of memory that stores memories over a timeline, so something like autobiographical memory. And this is interacting with an emotion engine, which is updating the emotion and mood of the character in a dynamic way. I was testing this virtual character, and also there's a physical robot from Hanson Robotics here in a teaching scenario. So we tested the system over 4 weeks, 2 sessions per week, like 20-minute sessions in a teaching scenario with a geography teacher. And we would like to look into what would be the effect of emotion and memory on the perception of the quality of the experience, measured with social presence and engagement, but also the task performance, so how people were learning and whether it is increasing the learning performance. And we indeed found that the robot condition with emotion and remembering capabilities made people to stick with the conversation longer. The novelty effect didn't disappear immediately, and it kept a conversation more interesting and increased the overall performance. I have been also working on situated interaction. So this is a virtual receptionist robot that is at the entrance of the computer science building at Utrecht University. The goal of this project was to automatically decide for this character which person to attend to. So it is basically a situated robot, so you want to see if people are approaching, which person is really interested in talking to the robot, because they can also be just passing by. So we would like we looked into several features coming from the microphone array and the depth camera, such as change of distance, orientation, maybe a greeting, waving hand, distance, closeness to the center of field, etc. So all the cues that we can capture, and we created a multi-modal model of engagement detection. It created an engagement score, and based on this engagement score, the gaze behavior of the robot was autonomously driven. And finally, I also worked on multi-party dialogue. That was a work on social practices theory, which is a social theory. Simply, I can explain it like when we are functioning in a social world, we have certain expectations of other people. For example, if you shake hands with someone, you also expect the other person to shake hands with you. So these kind of constructions you can create, and we created a multi-party dialogue engine to have these characters interacting with each other. That was a therapy scenario where it's a couple therapy. There are 2 people, and the user is like a therapist talking to these characters to manage this 3-party conversation, as an example. Okay, so I would like to slowly wrap up. So there are several challenges in this area. The first challenge is, because I'm always talking about data collection. creating an environment to collect the data, finding the right instruments, actors, actresses, pre-processing, post-processing the data is a quite challenging thing. It takes quite a lot of resources and also time. You can consider we can use 2D videos as well, but 2D videos, although they are widely available, it's not at the level of quality at the moment, these 3D construction methods for generating believable and convincing animations. The second challenge is sophisticated algorithms. Of course, deep learning algorithms are working very well for that, but they are black box algorithms. You cannot easily debug them, and they might be really computationally expensive if you have a lot of data. There is a gap between subjective and objective metrics. So what I mean by that is, for example, if you look at the computer vision community, there are clear benchmarks. So people are comparing to each other to let's say have 99.2% accuracy. So you have clear challenges and things like that. But in the area of animation, it's pretty subjective as well. For example, if you are generating audio-driven gestures, there can be multiple different type of gestures that are matching with this input audio. So comparing only to the using objective metrics or to the ground truth is not enough. And it might even be sometimes contradictory. So in animation research, we always do subjective and objective evaluations together. So we always ask the users or experts or animator how they perceive the animation quality. And finally, social signal processing in XR is an interesting area. So how to interpret the social and emotional states of users and how to generate automatic responses. There's quite some work done on social signal processing in human-robot interaction or computer vision. But what are the challenges in particular in VR or AR? This is still an ongoing area. In conclusion, virtual humans reach to a state where they can be modeled realistically, but realism in movement and interaction is still missing. Interactive applications requires on-the-fly generation of animation, so you cannot predefine everything, because if we are going to have social extended reality, we want these motions to be generated real-time on the fly. And perceptual studies are needed to understand what works for which type of applications. So it's not only about generating the motions, but we need to understand what is really working from the user's point of view, taking a human-centric approach. I would like to thank a lot of my collaborators and students over the years. Of course, it was not done alone. Okay, so here I'm going to show a video, and while it's playing at the background, I think I can accept questions. Thank you very much.
Thank you very much for a wonderful overview presentation. One of the challenges that people have in the university community of doing data-driven research is that often commercial organizations have much more data and have much more processing power and have many more people. Mm-hmm. In an area like this, the facial animation, for example, where there's a huge commercial interest in the Disney's, Pixar's, with massive resources, I would assume, and also a lot of touch-up artists who can correct any problems as it goes. If we look at the particular example of gaze tracking, it seems to me that are there private solutions that have solved this problem already, or is this still an open problem that requires public space solutions? Yeah. And gaze is just one. There are a whole bunch of these things. But can we still compete at a university level? I doubt that we can in the machine learning community, but can we do it in this space?
Mm-hmm, yeah, very good question. Thank you. So what is happening in the animation companies, like big animation companies? They have some R&D departments that also focus on that type of research, and they publish sometimes. And the community is more going towards publishing data sets and algorithms more openly. But it is not really like the animation industry is super advanced in that area, so there are still missing areas. But that is also true what you say, in a sense that, for example, when they are developing Avatar, they come up with new techniques always for facial expression capturing and generation, and all of these things are not always open to the public. So these are protected with commercial interests, of course. But there are also things that industry cannot do, or that doesn't have the resources or priority to do. And I think these are the things that the research universities can do. Ideally, we should collaborate. So that is the ideal. We should talk more to each other. So this is what I'm trying to do. For example, I talk with Guerrilla Games, PlayStation, Sony, this kind of people, to find out what their needs are and how we can really do things that is also helping for the needs of the industry.
Okay, and one last observation, because I just saw the piano player behind you. How much of this is psychology and how much of this is technology in terms of having convincing avatars? You know, do you really need to duplicate reality, or do you really need to fool people?
Well, when you are generating expressive animations, we always, as I said, compare to ground truth animation. So we try to be as close as possible to the ground truth. But the animations generated can be various, so it can deviate from the. It's better to use generative methods, like more probabilistic methods, so you can get some sort of variation and not some sort of repetition. So in that sense, you have some room for both objective and subjective metrics. So there's not like really a lot of benchmarking yet going on in this area. But we 2 years ago we started a challenge, a GenAI challenge. Which is a work that is aiming to benchmark gesture generation methods that is generated by different groups. So we can really do these comparisons. But there has to be a lot of talking and comparisons and benchmarking for this type of research, which is not really happening, because originally it's coming from the computer graphics animation domain, which was initiated by industry. And it was like, let's do something that works for this for particular scenario. And push the boundaries, and then if it is satisfying for the animators, it is good. But from a scientific point of view, we need more benchmarking and evaluation and comparison.
Okay, great. Thanks very much.
Maybe we have time for a couple more questions. Okay. Thank you for your presentation. And I want to ask a technical question about the gaze tracking one. And how did you, what device did you use to collect the data? Can it also collect data like the, for example, the pupil, like the diameter, this kind of? Yeah, thank you.
Yeah, we were collecting data both from upper body, so the movement of the torso, as well as the head movement, and also eyeball movements. We fed eyeball movements into the network as well, but that one was not producing very good results. So we were mostly focusing on the head generation and the body movement generation. But we have the data, so it can be more elaborated on that part as well.
Can I ask one more last question?
Sure.
Also about this project, do you think also the pupil dilation and for example the saccade, this kind of data is also important for virtual human?
Yeah, definitely. That was a gaze following behavior, but you can also have a saccadic behavior, like jumping on different type of objects. We actually created a setup to collect saccadic data as well. We put in the motion capture system a lot of cables and buzzers that make noises, and then so that we can capture this data. It was quite challenging because when there's sound, people are not very accurate about directing their gaze to the sound. So the sound is coming from here, but maybe they look there. So we have to find another way to collect more robust saccadic data rather than only using audio, maybe something like colorful objects and maybe a little bit training in advance the users. So that is something still to be explored, but if you have any ideas, suggestions, happy to talk further.
Thank you.
Is there any other question?
Hi. So first, thanks for this great overview. Yesterday we saw some demonstrations in the lab of CWI on volumetric capture approaches for representing real humans. Do you see some of those approaches, on the one hand volumetric capture and on the other hand animation, coming together in certain applications or directions? Can you reflect on that?
Yeah, definitely, yes. I think social XR is a very obvious application area for that. So if we can have, for example, audio-driven characters that are representations of ourselves, right, over a distance. Maybe we don't want to show our face all the time, and we can derive these avatars directly with audio and text. So my camera is not turned on or whatever capturing device. I just talk to a microphone, and my avatar kind of talks. So it's in the range of deep fakes. Sort of, but done in 3D and 4D. But of course there will be also some ethical considerations there if you have these digital copies of ourselves, which is a very, very important topic, I think.